We'll probably have 2 lectures on clustering, and everything will get pushed back on the schedule, and we'll probably just drop something as a result. Alright, so here was the main thing we left at the end of Thursday's lecture, was that we talked about splines on Thursday and smoothing splines in particular. This was the smoothing spline problem I wrote down at the top here. It's to minimize this criterion of raw functions f. Any function for which this interval is well defined. And so we take the squared error between y and f of xi, and we add to it lambda times the interval of k minus 1 over 2, that order derivative of f. We square that and take its interval. So here k is specified. It's some fixed order we specify ahead of time. The most common case is 3, so this would be a cubic smoothing spline in case 3. And so that would be the second derivative of f squared. I also should point out that k has to be odd, right? For this to make sense, k must be odd. So if somebody tells you that they have a quadratic smoothing spline, you know that you don't know what they're talking about. Because, right, so otherwise this doesn't make sense, this this derivative of f. Okay, so the main achievement with smoothing splines is that the solution to this infinite dimensional problem happens to be unique, number one, and number two, it's actually a natural spline with knots at the data points, x1 through xn. It's a natural spline in order k. So for cubic splines, for a cubic smoothing spline, when I solve that infinite dimensional problem, I can actually restrict my attention just to natural cubic splines with knots at x1 through xn. And then what we did last time is we actually parameterized f as a combination of the natural spline basis functions. There was exactly n of them because there's n knots. And so we wrote this in that finite dimensional form and we solved it. We saw it just kind of like a generalized ridge regression. And this fitted values ended up looking like this. Y max. These are the fitted values. So the values f hat of x, f hat of xi for I going from 1 to n look like this. N times n transpose n plus lambda omega inverse n transpose y, where n was this matrix whose columns gave us the evaluations of natural spline basis functions across the data points. So each column was taking one of those basis functions and evaluating it across the n data points. And omega contained something like the integral of their derivatives of or second derivatives of the products of the natural cubic spline basis functions. So these are all, it's all written down in the notes if you forget where these came from, but basically this just came from parameterizing that in finite dimensional form. And we saw that this we could rewrite as I plus lambda k inverse y. And on your homework, you're going to look at that k matrix there. Okay, so that was the main conclusion of last time. That's all we're going to say about splines. There's a lot more interesting things to say that we're not going to cover. I'll just say them verbally, kind of in words, and you can look up the references or you can ask about them later. Number one is that splines have all the same convergence properties as kernels do, essentially. So all the same convergence rates we learned for kernels also apply to splines. But with splines, you work with different function spaces. So with kernels, we assume that the function was what we call a Holder class. With splines, we assume that the true function is what's called a Sobolev class. And so the only difference is that we look at a class of functions f0 or f that satisfy the following property. If we take the kth derivative of f and we square it and we integrate it, if we're doing function estimation, say over 0, 1, then this has to be bounded by a constant L. So the set of all functions for which this is true is called the Sobolev space. I'll just write it here. Of order k with constant L. Okay, contrast this to the definition of the Holder class we have in the notes. You'll see that actually this is bigger. That the Holder class of constant k or order k with constant L is actually contained in this one. It's not hard to see that. But so smoothing splines converge at this rate, the same rate, n to the minus 2k over 2k plus 1 over this class. So they basically get the same convergence rates as do kernels over essentially the same class. It's a little bigger function class. So it's actually a little bit of a stronger result. Okay, that's one interesting property, that they both kind of have this, this fast rate of convergence over this function class. It means that as we assume more and more derivatives from the true function, we get faster and faster rates. It adapts to smooth and clear functions. The other interesting thing is that in a very interesting sense that is hard to make precise unless we were to study it in detail, smoothing splines are almost asymptotically equivalent to kernel regression, to kernel smoothing. So there is a choice of kernel that asymptotically leads to an estimator that looks very much like a smoothing spline. Remember, they're both linear estimates, or linear smoothers, so they both take linear combinations of y, right? And it turns out that you can show that this is almost like doing a kernel averaging, this operation here. And in fact, it's asymptotically equivalent to it in certain locations. And that kernel is also a very kind of unusual kernel. It's not the Gaussian kernel, it's not the, whatever box Neshnikov kernel. It's something very kind of odd. So that's another interesting result, that they're almost equivalent asymptotically to these lines of expressions. And I guess, yeah, so those are just two other things about smoothing splines that I want to mention that we're not going to cover. Any questions before we move on to the other types of kernels? Reproducing kernel number spaces? All right. Oh, yeah.
So, if that's a stronger result, like what's an example of when you would use smoothing kernels versus splines?
Smoothing kernels? Well, I think it's really a matter of maybe your background. I think most people in machine learning learn kernel smoothing as the kind of standard smoother or local polynomial smoothing. And smoothing splines are much more natural, I think, to statisticians. I think it's just a matter of background. They're very similar. They perform really similarly. And theoretically, they're very similar too. It's not that much bigger of a function class. I mean, they're really almost the same. So this is just an integrated bound, and the other one's a pointwise bound for the function class. The big difference is versus kernel smoothing and smoothing splines and adaptive non-parametric methods, locally adaptive non-parametric methods like wavelets. There's a huge difference between those two methods and these locally adaptive methods. And so I won't talk about them because we're going to run out of time, but you would use locally adaptive methods like wavelets when the true function that you think you might try and estimate looks something like this. It has an inhomogeneous level of smoothness. So in a case where the true function is smooth in some parts and wiggly in others, smoothing splines, kernels, in fact any linear smoother whatsoever, can't really do very well. And you can make that very precise mathematically. There's a beautiful paper by Don Ho and Johnstone that covers this, and it's referenced in the notes. Okay. So there's this kind of intermediate class of estimators we can consider before we move to RKHS, and we'll just think of that as like basis regularization. So imagine that we have an interest in problems of this form. H is some function class here. So it's we might imagine we have a basis for H. And J is a penalty here that penalizes. It's either you think like a roughness penalty or a smoothness penalty. It's going to penalize undesirable behavior and the fitted function f. So for smoothing splines, this is a particular case of an estimator like this, right? Where we took j to be the integral of some derivative of f squared. And so it did penalize wiggliness and not order derivative. And lambda, this tuning parameter, right, tells us how much emphasis we put on this penalty here. This is the data fitting term, right? So for small lambda, we'll be paying closer attention to making yi close to f of xi. So this is a pretty broad class. This is called basis regularization. Smoothing splines are one example where h is actually everything. It's just all functions for which that penalty j is defined. But in general, we could think of a different h and a different j, and each choice of h and j will lead to a different estimator. So RKHS, representing kernel Hilbert space, in that estimate is also of this form. And so it's another example of a basis regularization problem. And there's actually a lot of relationships between smoothing splines and RKHS through this notion of basis regularization. And so we may explore a bit. And so what we do in RKHS is that we start off with a particular function space that we're going to denote by h, and I'll use a subscript k to denote that this comes from a particular kernel. Okay, we call this a reproducing kernel Hilbert space. This function class is called a reproducing kernel Hilbert space. And how is it defined? Well, we start off with k. And we're going to do RKHS in just one dimension here. And so at the end, I'll talk about how to extend everything in higher dimensions. So k, it's a function from r cross r to r, which takes in two variables, two numbers. And it's a positive definite function. And I'll tell you what that means in a second. Called a kernel. This is unfortunately also called a kernel, so we'll call this a Mercer kernel to differentiate this from a smoothing kernel like we had for kernel smoothing. So after we choose this k, I'll tell you a couple choices. It generates a function space that I'll define for you, and then RKHS is just solving this problem with a very particular choice of j. So it's a basis regularization problem where we use this function space that's defined by this kernel. So we're fitting linear combinations of some special types of functions, penalize them in some special way. We'll make that all precise in a second. So some examples are, for kernels, are the polynomial kernel. K of xy ends up being x times y plus 1 to the k, for some order, polynomial order k. And so when we use this polynomial kernel, we get things that look like piecewise polynomials. This is probably the closest in terms of the way it looks to local polynomial smoothing or to smoothing splines of order k. Another example is the Gaussian kernel, or sometimes called the Gaussian radial basis kernel. And this looks like e to the minus a constant delta times x minus y squared. The two very common choices of kernel. Okay, so after we define our kernel, with the restriction that it be positive definite, we're going to define h in a very particular way. H is going to be spanned by functions that look like this, the sum of, what do I call them, alpha. So, in other words, functions in H look like linear combinations of kernel functions after I fix the second argument. So if I just fix some point y in R, then this function is a function of the first variable, so it's a univariate function. And if I just take, wait, that's not, if I just fix a bunch of points for the second argument, and I look at these all as functions of the first argument, and I take just arbitrary linear combinations of those, then any linear combination of kernel functions where I fix the second argument is going to be a function in my function space HK. So I should call this alpha m in R, and y m is in R. This set M could be infinite, it could be actually uncountably infinite as well. It could be a very large set. So for example, this function where I take, the function of x, I'll define it as, say, alpha 1 times k of x, y1 plus alpha 2 k of x, y2 plus alpha 3 k of x, y3. That's an example of a function that's in that function space HK. So that's how I'm going to define my function space HK. It's very, very big, as you can tell from this representation here. And now we're going to start reducing this problem. I'm also going to tell you what J is going to be. It's something that we can actually solve and understand in more detail. So the first thing we do is we're going to recall that, or I guess you can take this as a definition. This is called Mercer's theorem. So a lot of people recognize this as the starting point for reproducing kernel Hilbert spaces, at least mathematically. You can take this as a definition if you'd like. Is that a positive definite function has this the following expansion. I can write it as eigenexpansion of the positive definite function k. Think about it like an eigen decomposition you have for a matrix. So this is the analog in the function space. So if I had a positive definite matrix, I can always take an eigenexpansion where its eigenvalues are real and non-negative, right? This is the same kind of idea, except for it's a positive definite function. And so these are called the eigenfunctions, phi I of x. And these eigenvalues, gamma of I, satisfy the following property. They're all non-negative because it's positive definite. And they're square summable. Okay, so that's it's really going to be our starting point, so we can choose a kernel, any kernel satisfying that. And those two kernels we wrote down both satisfy this. It's called eigenexpansion. And okay, this means that actually I can represent any functions of this form that are in the represent kernel Hilbert space also in terms of the eigenexpansion. and I can represent them as just a linear combination of these eigenfunctions phi. Okay, so this is any f in the reproducing kernel Hilbert space, I can write in terms of the eigenfunctions phi. And these C's have a very special property also. These C's have to satisfy Ci squared over gamma I being finite also. So what I'm going to try to do is I'm going to try to give you a feel of what we can do with RKHS theory without trying to go through these mathematical details too strongly, because that would take us a lot longer than 20 minutes. So hopefully you won't be too bothered by the fact that we're just kind of skimming over some of the stuff. You can think about this also as a definition for HK. Set of all functions for which I can define them as linear combinations of the eigenfunctions phi, where the linear weights satisfy this square summable condition. Now I'm going to define a norm on the function space HK. So if I have any f that's in HK, I'm going to define a norm. And it'll just be exactly this guy here. So what happens when I take its weights and its eigendecomposition, I square them, divide them by gamma, and I add them up. And so this is going to be finite by assumption. Question?
For the second representation, do the phi i's, these functions, have to be of a specific form? Or the constraint is only for the C's? We can use any phi we want. They have to be orthogonal or something?
Yeah. Yeah, well, so they define an orthogonal inner product. So they are orthogonal with respect to the inner product defined by HK, which I'll define in a second.
Should it be just phi I x, phi I y, or should it be the inner product of? It's just a scalar product, right?
Scalar product. Yeah. Those are just real value functions. So this is all the meat we need to define representing kernel Hilbert space estimators, but lucky for you that once you see this and you believe all this math is true, we get something very special at the end. I think you can kind of see why people like to use kernels so much, and we'll try to touch on that. Okay, after all this, here's how we're going to define the referencing kernel Hilbert space estimator, RKHS estimator. So you give me a kernel function K, say you give me this guy, polynomial kernel. I define my RKHS estimator to be the argmin over all functions that are in the RKHS generated by K. Right, so say these guys. You want to think of this as the definition. And I do the usual thing, yi minus xi squared plus, and what's our penalty going to be? Well, it's most natural just to take the penalty induced by the kernel referencing kernel Hilbert space itself. Okay, this is going to penalize if these eigenfunctions have the property, right, that they represent different, say, levels of smoothness with respect to the kernel, then using this as the penalty will automatically kind of give us a smoothness penalty. So where does it come from? This is the RKHS estimator for non-parametric regression. It just looks like that. So it should be in parallel form. The smoothing spline is just a little more abstract in some sense, right? Because so like you can't get your hands quite on maybe what this is and what this is without a specific example. Okay, so this is infinite dimensional, typically, right? Because this kernel defines an infinite dimensional function space. But it has kind of an amazing property. It's like smoothing splines. And We call that in RKHS theory the representative theorem. Representative theorem. Really saves us. And what does that representative theorem say? It basically says that I can represent the solution to this problem as a linear combination of kernel functions where I fix the second argument. Well, that we already knew, right? That's just the definition of the reproducible kernel Hilbert space. It's a linear combination of kernel functions after I fix the second argument. But the representative theorem says that we can fix the second argument only at the data points, xi. And if we do that, then that actually, one of those will be the unique solution to this problem. So it's produced infinite dimensional, where we potentially have to look at combinations of kernel functions where we fix the second argument to be anything that's no value, any y, point ym. So just fixing the second argument to one of the input points xi. So it's an n-dimensional problem. So the representative theorem implies that there's a unique solution f hat to that problem. And furthermore, I can write it as this, in this form. F hat of x is the sum of alpha I, k of x comma xi. I equals 1 to n. So it really is a pretty basic result, just like the smoothing example. After this, let's suppose we believe this, and we'll prove this in a second. It's not hard to prove. After we have this fact, let's just define this matrix Kij. Hope you don't get confused by all the k's running around. K is the function. I'm also going to use it for a matrix just because it's convenient. It's a matrix that contains a kernel evaluated at xi and xj. Okay, so after I have that, look, I can write, in particular, I can write f hat at one of the input points xi as the sum of j equals 1 to n alpha j kij. Right, the kernel evaluated at xi comma xj. And so I'm just going to reduce basically this problem to one that's a problem in solving for the alphas. Solving only for the alphas, and then it's a finite dimensional problem. Again, we can actually solve in closed form because it's kind of like a ridge regression problem, and we'll see that the fitted values are again just a linear function of y. So I can rewrite the problem as the argmin over all alpha now that are just vectors in Rn, give me the coefficients of f in this expansion here. And I'll write the first term as y minus k times alpha squared. Right, because these guys, the components of this guy, just give me the fitted values right from that representation. And so I have yi minus f hat of xi squared, that's it, plus lambda times, well, what is that guy? So I don't know yet what that is in terms of the coefficient's alpha, but I claim, and I'll show it to you in a second, this is just alpha transpose k times alpha. Same matrix K. So the solution ends up being f hat, or alpha hat is k. Oh, I guess. So when I say positive definite, it's implied, by the way, that the function is symmetric. That's part of the definition. So I get the solution to this is k transpose k plus lambda k inverse k transpose y. But because of the fact that the kernel is symmetric, that just is, again, like I said, it's implicit, and we call it positive definite. This is really this k squared plus lambda k times ky. Right, if I move, for example, I move that kn, then I get k plus lambda I inverse y. Wait, that's not quite right, sorry. I get I plus was that right? Yeah. It was right, yeah. K plus lambda I inverse y. So again, it's just a linear function. The point is that it's just a linear function of y. Some matrix S times y. Any questions before I show you that this representative theorem is true? Yeah.
Are all kernel matrices invertible?
Invertible. Yeah, when we say they're positive definite, that makes the matrix K invertible.
Yeah. So if it's positive semi-definite kernel, is that even
if it's positive semi-definite, you can simply drop those bases corresponding to the zero eigenvalue. You can simply exclude them so that it can be reduced to always a positive semi-definite, positive definite.
Yeah, that sounds right, although I'm not sure how you always do that in practice. It may be kind of hard to identify which ones are have the linear dependency. But most times that you define kernels, they always result in a positive definite. Right? You're defining from a kernel function itself. So you would just start with a positive definite kernel function. All right, so this representative theorem is actually remarkably easy to prove. It's in the notes. I'm also going to do it here. You only have to believe a few things about RKHS facts that I'm not going to tell you, but these you can actually check. You can just check from these definitions. Take everything on the whiteboard or the blackboard as given. You can actually check the things that I'm not going to prove. There's a few facts. Okay, and I guess I will. Go ahead and do that in case there's less than any questions. So the first thing we do is we're going to make this actually a Hilbert space. So we need to define an inner product. How do we know what a Hilbert space is? Just out of curiosity. Okay, it's not that important. A Hilbert space is just a function space that's complete and has an inner product. And so we're going to give it an inner product. So we're going to note it like this by the inner product between functions f and g with respect to the RKHS HK. Because I had a norm somewhere up there. So we're defining an inner product on HK, it'll lead to the norm on HK as well. And so if I have F, which has this expansion, and if I have G, which has this expansion, right, so F is this linear combination of the eigenfunctions, G is that one, different CIs and DIs. I'm going to define their inner product as follows. I'm just going to take CI times DI over DI from the 1. Okay, and so the inner product of F with itself gives us the squared norm of F, and that just ends up being defined as the sum of CI squared over gamma. Okay, so it's, you can think of this just coming from the inner product of F with itself over the Hilbert space HK. Okay, and now these functions here, the kernel functions are fixed. The second argument at one of the input points, xi, have these very special properties, and these are called the representatives of evaluation. Called the representative of evaluation for the following reasons. Well, it's really just the first reason. I take any f that's in the Hilbert space, a representational Hilbert space. I take its inner product with this function. This is also a function that's in the RKHS, right? It's trivially in there because it's just 1 times itself. Right? Functions in the RKHS are linear combinations of things in this form. If I take the inner product of these two guys, then I get f of xi. I just get f evaluated at xi. So this you can check straight from the definition. I won't do this for you. That's really actually the key property. Now this is just a special case of, the second one is really just a special case of this first fact. And that it's, if I can, given that fact, I can actually write the norm of any function that's a linear combination of these representatives as alpha I, alpha j, k, xi, xj for any combination of representatives. Okay? So if I take linear combinations of just these guys, then and call that function f, then its norm is actually going to be just like this. The sum of alpha I, alpha j, kx, I, xj. And so look, that's just actually alpha transpose alpha. That just ends up being this, right? It's alpha transpose k alpha. So that proved for us that once we restricted our attention via the representative theorem to functions that were just linear combinations of the representatives, then the penalty term in that finite dimensional form was really just alpha transpose k alpha. I still have to prove for you now, though, that if I look at the original problem up there, then I can restrict my attention just to functions of this form that are linear combinations of the representatives. I still haven't shown that to you. But once I show that to you, everything will be done, right? Because all I do is I plug in that linear combination here, and this part is obviously what the loss term looks like, and the penalty term looks like alpha transpose k alpha from that term. So now we're going to show that if I have any function that's not a linear combination of representatives, but it's that plus something else, that has to achieve a strictly higher criterion value than just if I got rid of the something else and had only the representative part. Okay, so we have to prove that if I have this function, we'll call it f tilde, which is f plus rho. Let's suppose that f was a part that could be represented like a linear combination of those representer functions. So I can actually write out f is the sum of alpha I k xi. And rho can't. Rho is any other function in the Hilbert space that can't. Then f tilde gets a higher criterion value than f. Understand that once we've shown that, then we've proven the results.
Aren't we assuming here that like it's a linear combination of f and rho, right? Which is kind of restricting again ourselves to a specific class of functions. Because,
Rho could be anything.
but so what I'm saying is that it can be f times rho as well, right?
No. So you give me any function you want. Any function in the referencing kernel Hilbert space. We'll call it f tilde. I can always write it as f plus f tilde minus f. Just call that guy rho. Okay, and just now we're going to move a little bit. We're going to progress a little bit from here. We're going to say that f is, linear combination of representers. And rho is orthogonal to representers. Why can I do that?
You can project f tilde to the subspace and to the orthogonal complement of the subspace. And
Right.
It's
So these two things are going to span the entire function space. If I have any kind of subspace, if I look at things that are in that subspace and things are orthogonal to it, then when I take their sum, then they're going to equal the full function space. I can always get something in here by just projecting f tilde onto the set of linear combinations of representers and projecting something onto the orthogonal set. All right, so now that I have that, I'm going to claim, first of all, that when I evaluate f tilde at the points xi, it gives me the same value as f. So that, in particular, they're going to actually achieve the same loss term. So when I go back to that criterion and look at yi minus f of xi squared, it's going to be the same thing as yi minus f tilde of xi squared. So I'm going to prove that each one of these is equal to each one of those. And that's actually quite easy. Right, just by definition, it's f of xi plus rho of xi, which I can write out as f plus rho, inner product of that with the kernel function. Right, because by the first property there, take an inner product of this kernel function, evaluates this function at the point xi. And now, well, by linearity, I can split this up, right? Any linear inner product is linear, so I get f of xi, it's kind of what we had before. Or I guess I'll just write it like this, so you don't think I'm skipping any steps. Inner product of f with the kernel xi plus the inner product of rho with k of xi, but this part's just 0. Right, because by assumption, rho is orthogonal to all those functions. So this whole thing is just the first term, which is f of xi. Okay, so now I've shown that actually f tilde and f have the same loss. All I need to show is that the penalty achieved by f tilde is larger than the penalty achieved by f. Right? Once I've shown that, it shows that f has a smaller criterion value. Okay, so let's just look at the penalty. So that's the norm squared of f tilde, which I can write as the norm squared of f plus the norm squared of rho plus, well, what's supposed to come here is supposed to be, right, 2 times the inner product of f and rho. But again, that's just 0, because rho is orthogonal to the representatives of evaluation. This is the linear combination of those representatives of evaluation. In fact, we're already done, right? Because this is the penalty, so this is just going to be, it's strictly bigger than f of hk squared. And it's only equal to it when rho is 0. And so when rho is 0, f tilde is, in fact, f. So it's a linear combination of the representatives of evaluation. Okay, so that's all the proof is for representative theorem. It's an amazing theorem which has a very kind of, in hindsight, a very easy proof. Yes?
You don't use the square outer norm to measure the function's norm and the arrow to the representative theorem.
Good question. You know, kernels are very specialized to that choice of norm for this reason. If we used a different choice of norm, well, we have to define a different norm on the function space, right? So the most natural measure is just to take the inner product that's defined and square it. So I'm not sure what else we would use.
Isn't this the only norm that is induced by inner product in variables?
Yeah, that's essentially what I'm asking. I'm not sure what other norm we'd use. Anytime you're confused in functional analysis by, like this is a norm squared, an inner product, orthogonal, all these terms, if you're confused, just pretend like it's linear algebra. Just do everything in finite dimensional case, and then worry about it later whether what you've done holds or not. But 99.999% of the time it's the same. You know, things being orthogonal, norms, inner products, it's just entirely the same between function space and finite dimensional space. And you can thank the people who created the function spaces for that. I'm sure that they worked in the theory very carefully and defined things so that it all works out that way. So people in functional analysis worry about that, but you can mostly just treat it like it's a real vector space. So did I erase the problem? I guess I did. Here's the really nice thing about RKHS. In a nutshell, write down the problem again. It ended up being like this, right? It's to minimize this over alpha. And the solution was, unless I got it wrong, k plus lambda I inverse y. That was what y hat was. Where k is kij is our kernel function between xi and xj. The really nice part about RKHS is that all we have to know is the kernel matrix in order to compute the estimate. That's all we have to know. Look, it pops up here and here in the problem, and here in the solution. So all I need to know is how to just talk about a kernel between points xi and xj. Right, think about it like actually, did I erase the other ones as well? I guess I did. A similarity measure between points xi and xj. Right, so here was one possible definition is e to the minus delta xi minus xj squared. That's one possible choice. Okay, even when I'm doing basis regularization, I don't have to come up with basis functions. They're already taken care of for me. I don't have to specify what the basis functions are. I don't have to, think about what the basis is in terms of some analytic form. All I need to know is how to evaluate kernel between xi and xj. Similarity measure. Once I know that, I can actually solve this problem and get a fitted value for the estimate y hat. Why is that nice? Well, let's suppose we're doing non-parametric regression now, but where xi is no longer real valued or even an RD, but each xi is a word, or it's a picture, or it's a movie, or it lives in some weird space. It would be very hard to come up with basis functions that span some space of desirable functions. That would be very, very difficult, a very challenging task. But as long as I can come up with a similarity measure between inputs, I can say this word and this word are this much similar according to some measure, I can actually estimate, I can perform non-parametric regression of y on those features. So people call that kernelizing the input space. As long as I can kernelize the input space, describe what this means for my problem, a of xi xj, I can get an estimator. The same trick holds with outside of non-parametric regression to non-parametric classification, kernel PCA. All these things follow the kind of the same paradigm. You only need to kernelize the input space. So maybe the radial basis or the Gaussian radial basis kernel is no longer appropriate, but maybe you can think of one for your particular input space. Questions? Yeah.
Yeah, continuing to F tilde, you said F tilde is F plus rho, which means F tilde doesn't line the kernel with linear combination of
The representatives, yeah.
Yes, but then later on you represent as a linear combination of the kernel. F plus rho dot beta k.
Sorry, I didn't quite follow the question.
So first of all, you start with the rho, and you're saying that F tilde doesn't line linear combination of the kernel. Right.
Of these guys. It doesn't lie as a linear combination of these guys, the representatives of evaluation.
Right. And then later on you represent F plus rho as a
Down
linear
here?
combination. Yes.
But this holds for any function, not only function. This is, should have written that down. Any function in HK, this is true for any in HK. The second one is true for any f that's a linear combination of representatives. This first property is true for any function that's in a reproducing kernel Hilbert space. So better, maybe a visual picture is like HK is huge. It contains a lot of functions, and the representative evaluation are small. They're just like some small subspace of that. So we're trying to prove that the solution to the big problem over all of this is actually an element of that guy. But that first property holds for any function in the big function. Let's take a break, unless there's another question.
I was just wondering, so do you end up like sometimes having to optimize over what kernel you choose?
Good question. Sometimes people, so first of all, lambda is a smoothness measure on the function, right? So we're still having to optimize over that typically. Optimizing over the choice of kernel is a little more tricky. Certainly people are ambitious and try to look at what happens when they use many kernels. But maybe because we don't have a lot of time, I won't get into this, but certain kernels are good for certain problems. Like the polynomial kernel is especially good for non-parametric regression. If you're doing classification and you think that the input space can be separated kind of in a radial fashion, then you might use the radial basis kernel. And so there are different applications call for different choices of kernels. But certainly people try different kernels and see if they can optimize the accuracy of whatever the estimator is. Yeah.
to add to that, is there a notion of sparsity in kernel space? Like, can we add?
Another good question. Yeah, so people actually look at what's called a so when people do kernel SVMs, you can do a sparse or one norm kernel SVM, but it only works with certain kernels. It doesn't work with the generic kernel. In fact, it's really just the linear kernel, or things that are very close to the linear kernel, that it works, for which it works. So sparsity is not, as far as I can tell, it's not generally kind of in agreement with the generic kernel. It only kind of works in special cases. Good question. All right, let's take a break and then we'll race through the rest. One or two. I just don't have enough time to tell all of them. So we'll have a lot of jokes for the next few classes. I'll just tell one. Which one should I pick? Oh, so we learned RKHS, so I'll tell this one. Colonel Hilbert. Colonel Hilbert was a very famous army general. He's one of the most famous of his time. And he was mortally wounded in battle. And the army scientists, they rushed to try to clone him so that his leadership could continue on throughout the war. And these army senior officers were really kind of perplexed and said, how is that possible? Aren't there an infinite number of parameters? And one of the army engineers explained, don't worry, we built a reproducing Colonel Hilbert space. All right, so it was timely, I'll have to give you that. At least it was appropriate. We have like 5 or 6 more to tell next time. So the class of linear smoothers, this is a very, very big class. This has covered everything we talked about so far. KNN, believe it or not, kernel smoothing, local polynomial regression, smoothing splines, and RKHS theory. All fits into this class. Y hat is just a matrix times Y. That matrix, obviously, there's a lot that goes into choosing that matrix. That's what separates all of these methods. This matrix can depend on x1 through xn. It does in all those examples. It depends on the input points. But still, once I fix those input points, Y hat is just a linear transformation of the observed outputs, Y. Okay, so this is a very broad class. There's a lot we can say about this class, and so we're going to kind of study a few properties of it. It helps to look at it in generality. The very first property we're going to look at is what we call degrees of freedom. Of an estimator F hat. That's in one of these classes. It lies in this class. So degrees of freedom is a concept I think we'll revisit later in the course, and I'll derive degrees of freedom a few times for various estimators. In general, if I wanted to find it for a function f hat, for some fitting procedure f hat, then it's 1 over sigma squared times the covariance between f hat I of y and yi. Okay, let me actually write this as G so you don't get confused. I don't want to. I can talk about the degrees of freedom of any function G. G is a function that's going to go from Rn to Rn, so that y hat is going to be G of y. Okay, so let's think about the inputs as fixed. We're in the world now where the inputs x1 through xn is fixed. All that's random is the y's. the y's come from some model where, say, I'll think of them as being equal to some mean plus error. Right? That mean mu could depend on the x's in some very complicated way. Doesn't matter. Epsilons are going to have mean 0, and the covariance is going to be sigma squared I. So the errors are mean 0 with 0 correlation between them, and they have the same marginal variance. And I'm just going to take that y that I get, and I'm going to apply some fitting function to a g, and it's going to give back y hat. The degrees of freedom of that fitting procedure g, we define like this. It's the covariance of the ith fitted value. So this is y hat I with yi, added up, divided by sigma squared. So the more covariance there is between y hat I and yi, the more influence the ith observation has on the ith fitted value, the higher the degrees of freedom. So we think of degrees of freedom as the effective number of parameters that's used by G. So it's a measure of complexity of the fitting procedure. Okay, again, we're just in a world now where we're imagining x as fixed and y as non random. I think it'll help us see some examples. So we're in the class of linear smoothers, so we're going to look at let's just look at this guy. The fitting procedure that takes a matrix and multiplies it by y. And so what's the degrees of freedom of G here? Well, it ends up just being 1 over sigma squared times the sum of SII. That's all it is. That's the covariance of the ith component of this with yi. Or in other words, it's just the trace of S over sigma squared. No, I'm sorry. This sigma squared goes away. Right, because y, each component of y has variant sigma squared. So it's just a trace of S. Conclusion. You use your favorite method, smoothing splines, at some value of lambda. Just fix some value of lambda that you chose, and anyway, cross-validation, whatever. If you want to know what the effective number of parameters that are used by that method, take the trace of that linear operator. Remember, for smoothing splines, it was like n times n transpose n plus lambda omega inverse n transpose, whatever. That linear operator, take its trace. That gives you a measure of its effective degrees of freedom, the number of parameters it uses kind of effectively. How about RKHS? Same thing. Just take that matrix, take its trace. This will give you a notion of, like I said, the effective number of parameters used by that fitting procedure, so that you can compare fitting procedures against each other that are not kind of on the same scale with respect to their tuning parameter values. Right? Because if I want to compare, say, smoothing splines to kernel regression or to RKHS or to whatever else, then I don't have a good way of doing that if they all have different tuning parameters. But if I kind of put them on the same parameterization with respect to degrees of freedom, and make sure they all use 10 degrees of freedom, then that's more or less putting them on equal footing for a comparison. This is a very nice thing about linear smoothers, that it's trivial to compute the degrees of freedom. Right? It's just the trace of the smoother matrix. In general, when G is not a linear function, it's very hard. So getting to know the complexity of a fitting procedure can be an entire research endeavor. It's very hard. But for linear smoothers, it's trivial. Okay, degrees of freedom is nice for the intuitive notion of effective number of parameters, right? Putting things on equal footing, etc. There's also a kind of more mathematical reason to want to study it, and that's the following, is that it tells you exactly what the optimism of a fitting procedure is going to be. Okay? Or another way of saying that is that it gives you a way of doing unbiased risk estimation. So let's suppose that, I'll just rewrite that model so you have it in your head. That's the model. And let's suppose I fit y hat, some estimate of y, and I want to know what the risk of y hat is, L2 risk. The expectation of y hat minus mu squared. Then I just play this very simple trick. I'll introduce y and subtract y. Then I get that it's the expected value of y hat minus y squared, L2 norm, plus the expected value of y minus mu squared, L2 norm, plus 2 times the covariance between y hat minus y and y minus mu. Okay, what's that? That's just the training error. It's the expected training error. Right, that's just the expectation of y hat minus y squared. This guy is just n sigma squared. Right, because y comes from this model. The expected value of the error, of the components of the error squared. This guy, that was a little sloppy. I didn't write that correctly. There should be a trace here. This is plus 2 times the trace of the covariance between y hat minus y and y minus mu. Right, this can't be just the covariance because that's a matrix. Not all the stuff is real right. So let me just look at this first term. It's the trace of the covariance between y hat minus y. Actually, I'm going to split up into 2 things. Yeah. Covariance of y hat with y minus mu. 2 times the trace of the covariance between y hat. And I can just write that as the covariance between y hat and y. Right? There's no point in having that minus mu there. That's redundant. And then the second part, I get minus y and y minus mu, the trace of the covariance of that. So that's just the covariance of y with itself. And I get a 2 in front, or it's really y with minus y. So it becomes n sigma squared times minus 2. So this one cancels with this 2. What's that? That's actually just the degrees of freedom. Right, so what I get is that it's the expected value of the training error plus, or rather minus, n sigma squared plus 2 times sigma squared times the degrees of freedom of y hat. So conclusion is, if we know the degrees of freedom, then we know an estimate. We actually know, yeah, we know an estimate for the risk, right? Because if I just take the observed training error, which is y hat minus y squared, and I just subtract off n sigma squared, and I look at, and I add to this 2 times sigma squared times the degrees of freedom of y hat. And I call this r hat. Right, it's a random quantity. Then the expected value of r hat is just the risk. Right? So for For linear smoothers, that's just the trace index. Very useful formula. Sometimes this is called the CP formula for when it's seed regression. It's related to Stein's unbiased risk estimate, which we'll study at the end of the class. It's an alternative for choosing the tuning parameter value, right? Now, for every value of the tuning parameter, I have an estimate of the risk. I can, instead of using cross-validation, this is computationally much cheaper. All I do is I take the training error, subtract off n sigma squared, add 2 n sigma squared times the trace of the smoother matrix, gives me an estimate of the risk. I can choose the tuning parameter like lambda and smoothing splines to minimize that. Questions? Yeah.
Could you give an example of a nonlinear smoother that's commonly used?
Yeah, sure. I mean, we didn't talk about this, but wavelets are the biggest example.
Okay.
So wavelets take the input, they multiply it by some matrix W transpose, it's the wavelet basis, and I take this and I perform threshold. Threshold this value, this vector, which means that I look at its elements and I set them equal to 0 for small and I leave them untouched if they're big, in absolute value. And I call that theta hat. And then the wavelet estimator is just y hat is W theta hat. So that's not a linear operator. Thresholding is not in any way a linear operator. Any other questions? Yeah.
So in this question for race, how do you estimate sigma square?
Great question. It's not always clear, but there are kind of a variety of ways that people try. So first of all, that's not a question that there's a generic answer to that make everybody happy, depending on the context. But one thing you could do, for example, is you could, first of all, it's generally probably better to overestimate sigma squared than underestimate sigma squared. So you could err on the side of overestimating it, and you could look at, you could fit a lower degree of complexity fit to the data, and estimate the residual sum of squares that are on that fit. And that might give me an estimate of sigma squared. Right? If I take a lower complexity fit by something that's not quite as wiggly, then I'll probably overestimate sigma squared, and it's probably better to err on that side than estimating too small.
So generally, like there's an expectation to have a training error is used to tune this parameter.
I'm sorry?
So standard way, like whatever the one is now, we directly use predictive value of training errors to optimize the parameter. But here we have experiments.
Oh, no, not the training error. If I use the training error to select the tuning parameters, then that would be, usually it would be disastrous because it would only look better as I make the model more and more complex. Right? For example, with k nearest neighbors regression, if I took k equals 1, I get a training error of 0. So it only looks better the more complex the model. We talked about using cross-validation to select the tuning parameters. This is an alternative to cross-validation that doesn't require any really additional computation. Other questions? All right, so it looks like I'll have to impinge into Larry's question lecture and just tell you for 10 minutes about high dimensions. But the answer is additive models. That's the end of the story. We'll just do a sequence of being very close. It's really the best idea.